The main greenhouse gases that we've got, they come into two categories. The first ones we've got is carbon dioxide, methane and nitrous oxide, which are the main ones that are emitted from fossil fuels and agricultural use and fertilizers. Then we've got 4 different F gases, and F gases are man-made gases, and they're used in refrigeration. They're also used in electrical circuits. According to the Kyoto Protocol on greenhouse gases, these are the ones that are actually accounted. And the lion's share, as you can see here, is carbon dioxide. And all the different greenhouse gases, they all have completely different characteristics. So you can't compare like for like because of the chemical compounds. Just to give you an example, we compare everything, it's down to the global warming potential. Carbon dioxide is a very, very weak greenhouse gas. CH4 is methane. Over 100 years is 28 more times potent. Right, and then we get all the way down to the man-made gases, sulfur hexafluorides. It's 23,500 times more powerful. So if you hear about F gas, this is what they're talking about. They're talking about man-made. So in terms of parts per million, we can actually work out in the atmosphere how many parts per million we've got of different gases. And as I said, the lion's share is carbon dioxide. And carbon dioxide predominantly comes from fossil fuels. Coal, oil, gas, different fuels that you hear of that are fossil fuels will all relate back to one form or the other. What's the problem? Well, emissions from fossil fuels are literally skyrocketing. We are addicted to hydrocarbons. The amount of energy that they give us has created our society that we live in. It's created our the houses that we have, the cars that we drive. Everything that we've got is owed to hydrocarbons, and we're now understanding the actual costs and the problem of burning fossil fuels. What we need to do is greatly reduce fossil fuel to pretty much zero. This is the pain that we have to go through. We can actually measure exactly how much carbon dioxide, CO2, is in the atmosphere. We're at now, I think, 416 parts per million. This is like nearly double what it was. CO2 has been constant in the atmosphere for about 3 million years. We know that from ice samples. Trundling along, we hit boom times, we get really good at extraction methods, population explosion, and all of a sudden, it's going through the roof. Not only CO2, but also methane is rising as well, and also F gases are rising. A quick crash course in carbon cycle. What we've got 2 different carbon cycles. We've got the long carbon cycle, and we've got the short carbon cycle. So the long one is where coal, oil, gas come from. Over millions of years, it gets sucked out of the atmosphere through trees, all different forms of life, and through millions of years, it compresses and forms fossil fuels. So what we're doing is we're extracting the fossil fuels and we're releasing it into our short-term carbon cycle, which is over here. I've got 2 different charts here. This one here is taken from David McKay's book, which we had to read going to college. You can actually get it online, you can download it for free. You've got some difference of figures here. You got in the atmosphere, you got 600 gigatons. In a more recent one, it's 800 gigatons. That's because of all the fossil fuels we've recently burnt. What's happening is we're upsetting the balance. So when we burn fossil fuels, we burn carbon, it goes into the atmosphere. And naturally, the oceans and the soils and the forests absorb vast amount of it. And then there's a little bit left over. And that's what we're having, like the 416 parts per million. It's increasing ever so slightly to a devastating effect. Whatever's in the atmosphere, we have this area just here that the near surface in the sea, it actually balances. So there's a slow cycle that it will actually catch up. So if you have 416 parts per million, a similar amount ends up here in near surface. Then in the deep parts of the ocean, it actually takes hundreds and hundreds of years to actually filter down. So there's almost like it's a barrier. It's almost like a concrete barrier that it can't go through. And we've, as humans, have now upset this natural cycle. So this is why we need to actually, not only do we have to stop burning fossil fuels, we have to figure out ways of decreasing the amount that's actually in the atmosphere. At the moment, we're burning through 52 gigatons. a year. That's including methane and the other greenhouse gases. We could be even increasing it at today's rate. We need to halve in the next 10 years is what we need to do. And by the mid-century, we have to actually have totally stopped burning and extracting all forms of fossil fuels. And the question is, how are we actually going to do it? At this moment in time, just 4% of the world's energy comes from renewable energy. We've got another nearly 7% from hydro. It's still renewable energy, but it's counted different. So if you add this and renewables together and nuclear, it's about 14-15% of the world's total energy demand. So we've got a huge amount of work to do, like absolutely colossal amount of work. It's just, it's a little bit scary really. So today's talk is, I'm focusing on one part of it, which is decarbonising the grid, and it's decarbonising the electrical grid. So we've got several different types of grids. In this country, we've got a gas grid, and we have the electrical grid. All right, so this is a picture of the control room that you have in the National Grid Centre. It's highly complex. You're going to have like a big energy source, like a nuclear power plant, or a coal fire plant that produces vast amounts of energy. It goes through a process. It uses a lot of energy at the start. There's a lot of wastage around this area. When the energy is getting transmitted, there's also more wastage. And then by the time it gets to us, there's even more wastage because we leave lights switched on. The whole system itself has huge amounts of wastage to it. To give you an idea where we are now in the UK, this is 2008 when the Climate Change Act got announced, which was quite amazing. What you see here is you got the actual energy for the whole country being used, and you can see it's on this nice decline that's going down. So from 2006 to 2019, we've seen this nice slow decline. So LED lighting has reduced the amount of energy, and people becoming aware of actually not wasting electricity, and also a lot of processes that we do is getting more and more efficient. As you can see, coal is actually starting to phase off, because one of the easiest ways of decarbonising the grid is to get rid of the dirtiest form of energy, which is coal. So when you burn coal, it's a lot dirtier than burning oil, and oil is a lot dirtier than burning gas. So they release different amounts of carbon into the atmosphere. This is natural gas, which is pretty consistent. For the future, they're still going to be relying on natural gas, looking at the different papers that have been released by the government. Then we have nuclear. We're going to have a lot of nuclear getting decommissioned, and there's a lot of nuclear coming back up online. And then all the way down here, this little grey area here, that's starting from nothing and starting to get like as you can see, it's growing in size, is renewables. And that's a mixture of wind, onshore, offshore wind, and solar PV mainly. And then we've got bioenergy, which is a little bit of a grey area, because a lot of bioenergy in this country is actually, it's waste. So we're actually energy to waste, but it's counted as a form of energy. And we've got some pump storage, and then we've got interconnectors that we get electricity from France, from Ireland. So to give you an idea, last time I did this talk, the amount of CO2 that we had, the current carbon intensity of the grid was 203 grams of CO2 per kilowatt hour. So in 2013 to 2017, we've managed to decrease the carbon content of our electrical grid by nearly half, which is quite amazing. So the electrical grid is actually doing very well decarbonising. The gas grid is not being decarbonised at all. Transport's not being decarbonised at all, and agriculture. Don't just take these figures that we're actually doing pretty well. Skip ahead to today. I took this screenshot a couple of hours ago. You can see we've just had a storm, and 27% of all the electrical energy in the United Kingdom is being produced by wind, which is actually quite amazing, And then also, you mightn't think it, we've had a 6% by solar today. Over a third of our electrical grid today was being produced by renewable energy. So that's quite good. We've got a hydro who's topping us up a little bit. We've got nuclear, which is a base load. It's very hard to switch on and off nuclear power plants, so there's always a base load of electricity coming from them. We had some of our imports. This is the interconnectors coming in here. We've still got coal on our grid, which is quite dirty. So the current carbon intensity was 155 grams per kilowatt hour compared to 203. So you can see it actually varies quite a lot. You can see here that we're actually, we're getting in the right direction for renewable energy, but we're not getting there quick enough. Carbon capture and storage, I call this the unicorn technology. Our fourth and fifth carbon budget in the United Kingdom is all based on carbon capture and storage technology. The reason that we're still extracting fossil fuels is because of carbon capture and storage technology. I think it's 1.7 trillion since the Paris Accord has been signed, has been put into extraction of fossil fuels. What they're claiming is that we're moving towards using carbon capture and storage technology so we can continue burning fossil fuels. There's only a couple of plants around the world that they've tried. It does work. They haven't tried it on scale. It's very, very expensive to do. There's three main types: post-combustion, pre-combustion, and oxy-fuel. I don't know too much about it, but one's extracting the carbon before you burn it, the other one's extracting the carbon after you burn it, and the other one's using kind of some oxygen type process to burn it at a different rate. Again, our whole future is actually now relying on this technology. So airport expansion, the reason we say we're going to reach zero carbon by 2050 is because of carbon capture and storage. I'm not an expert on it. I can't comment too much about it, but from just reading about it, it just sounds like it's too much to kind of like put the future of the world into technology that hasn't been proven on scale that's actually needed. And the actual cost of retrofitting all our thermal plants, is about £1 billion per plant. So it's very expensive. It uses a vast amount of energy. The other one that we're looking at is bioenergy carbon capture and storage. This one comes up of using fast-growing crops, and again using a process of extracting the energy, changing it into a biofuel, synthetic fuel, and you burn it, and then you bury some of the excess carbon. It's unproven at scale, and we're relying very, very heavily on this in the future. So it's something to be aware of and become opinionated about.